Okay, let's unpack this. If you've been following the AI space at all recently, you've probably noticed this
A
trend.
troubling one, yeah.
It feels like for the last year, the gap between the big proprietary models,
Mm.
your GPT-5s, your Gemini 3.0 pros, and the open source community has just been getting wider.
It absolutely has. That performance gap is real. And if you really peel back the layers, it boils down to three core problems that the open community has been struggling with.
Okay, what are they?
Well, first, there's architectural inefficiency, especially with long context. Second, a huge underinvestment in compute during the post-training phase, which is where the real refinement happens.
Kind of fair.
The third is a big lag in generalizing for complex AI agent tasks.
Yeah, right. And that's where DeepSeek-V3.2 comes in. This new release from DeepSeek AI isn't just another update. It feels like a really deliberate push to close that gap.
It is. It's a statement.
So for this deep dive, we're going to get into the three big technical breakthroughs they used. This new thing called DeepSeek Sparse Attention, a massive scaling up of reinforcement learning, and a new way to create agent training data.
And you have to understand, this isn't just theory. The sources we have are showing that the high compute version of this model, they're calling it DeepSeek-V3.2 special, it didn't just catch up.
No.
It achieved gold medal level performance in the 2025 International Mathematical Olympiad, the IMO, and the International Olympiad in Informatics. I mean, we're talking parity, or even better performance than Gemini 3.0 Pro in those specific high-stakes domains.
That's a foundational shift.
It really is.
Wow. Okay, but before we get to the gold medals, we have to talk efficiency. Because all that intelligence doesn't mean much if you can't afford to run it. The sources are pretty clear that the old way, using vanilla attention, was a huge bottleneck.
The biggest bottleneck. Traditional attention mechanisms, I mean, the things that let the model see how every word relates to every other word, they suffer from what's called $, computational complexity.
Okay, so break that down for those of us whose advanced math is a little rusty. What does otolde mean in the real world?
Think of it like this. If you have a sequence of text, say length, $11, and you double that length, the amount of computation you need doesn't just double, it quadruples.
Quadratic problem.
Exactly. So if you're trying to process a huge document, 100,000 tokens or more, the cost it explodes. It makes long context incredibly expensive and slow to run.
So DeepSeek's fix is this DeepSeek Sparse Attention, or DSA. It sounds like they're replacing that exhaustive check with something more surgical.
That's the perfect way to put it. They managed to crush that complexity down from 022, and that little dollars is just the number of tokens the model actually selects to pay attention to, which is, way smaller than the total length dollar.
It's like polling a few key people instead of the entire stadium. So how does it actually decide which tokens are the important ones?
It uses this clever two-part system. First, there's a component they call a lightning indexer.
Lightning indexer.
Yeah, it's basically a really fast, lightweight attention mechanism that does a quick scan of the whole sequence to get a rough idea of what's relevant, a rapid screening process.
Okay, so it flags the potential candidates. Then what?
Then the second part kicks in, the fine-grained token selection mechanism. Based on those initial scores, it goes and retrieves only the key value information for the top scoring tokens. So it's not wasting cycles on irrelevant fluff. It focuses only on what matters.
And the sources show this has a real-world impact. They ran it on H800 GPUs, and the cost per million tokens for long sequences was way lower than their last model, V3.1 Terminus.
A huge cost reduction, but here's the kicker, the part that really matters.
Right. Did they lose performance?
No! That's the thing. This efficiency gain didn't cause a performance drop. In fact, on dedicated long-context reasoning benchmarks, like AALCR3, the new sparse model actually outperformed the old dense one.
So it's cheaper, faster, and better at long-context reasoning.
It's a massive win, a huge architectural achievement.
Okay, that proves efficiency doesn't have to mean dumber. But that brings us to the second big problem you mentioned, the lack of computational muscle in that post-training phase. Why have open models historically skimped there? Is it just the cost?
It's a mix of things. Cost, yeah, but also stability and just expertise. Reinforcement learning is notoriously difficult to scale. It's expensive and it can easily collapse.
So the big proprietary labs invest heavily because that's where you sharpen the model's intelligence.
Right. They know RL is where the model really learns to follow instructions and align with human preferences. Open models traditionally might spend maybe 1 or 2% of their pre-training budget on RL.
And DeepSeek.
They changed the game. They allocated a post-training budget of over 10% of the pre-training cost.
Wow, that's a colossal commitment.
It's a total philosophical shift. It says post-training isn't an afterthought, it's a core part of the process. And they could only do it because they built a new, stable RL protocol based on something called Group Relative Policy Optimization, or GRPO.
Okay, hold on. Stability is key here. When you scale RL that much, you're introducing a ton of risk. You mentioned this term, policy divergence. What does that mean, and how did they stop the model from, going off the rails?
Policy divergence is basically when the model's behavior starts drifting too far from what it was originally trained to do. It can lead to really weird, unstable outputs. To prevent that, they use some clever strategies like off-policy sequence masking.
An off-policy negative sequence. What exactly is that? What kind of bad behavior are we talking about?
So an off-policy negative sequence is a data sample where the model took a really bad action, but it was generated by an older version of the model. If you keep training on those bad examples from the past, the new model gets confused and destabilizes.
Ah, so the masking just filters out those confusing, counterproductive examples.
Exactly. It makes sure the model is learning from good, relevant samples, which keeps the whole process stable.
And since DeepSeek is a mixture of experts model, they needed special stabilizers for that too, right? These keep routing and keep sampling masks.
You got it. MOE models are like a team of specialists. If you change things too fast, the model can forget which specialist to send a problem to. These masks basically preserve that internal routing table, ensuring the model stays consistent with itself as it learns.
And that massive stabilized investment is what really paid off. The core V3.2 model is now hitting performance similar to GPT-5 High on reasoning. But the real headline is the special version.
The special variant is the proof of concept. They took that huge RL budget and focused it exclusively on high-quality reasoning data. They optimized for deep thinking, not just long text.
And the result? Gold medal parity with Gemini 3.0 Pro in competition math and coding. I mean, that's a level of deep reasoning that we all thought was purely proprietary territory.
It really validates the whole idea. It shows that if open models can match the resource investment in post-training, they can achieve frontier performance, at least in these really demanding reasoning tasks.
Which brings us to the third big gap, the agent gap. Open models have always lagged in following complex, multi-step instructions for agentic tasks, mostly because they just don't have that fire hose of real user data to learn from.
That's the core problem. And DeepSeek's solution was, well, pretty brilliant. They decided to bypass the need for real user data by creating a pipeline for large-scale agentic task synthesis.
They just generated their own training data.
Systematically and at an incredible scale. We're talking over 1,800 different environments and 85,000 complex prompts. And the key was focusing on tasks that are, and this is the important part, hard to solve but easy to verify.
That's the sweet spot for RL. The trip planning example in the source really highlights this. Can you walk us through that?
Sure, it's not just plan a trip. It's a multi-day puzzle with cascading rules. For example, you have to use non-repeating cities, hotels, and restaurants.
Okay, that's already tricky.
But then it gets really complex. The cost of your hotel on day 2 actually dictates your budget for day 3. So if you pick a luxury hotel on day 2, say over 800 yuan, then on day 3, your total restaurant spending must be under 350 yuan.
Wow.
And those restaurants both have to be rated 4.0 or higher. And your attraction ticket has to be under 120 yuan.
That's a highly nested logical puzzle. It requires tool use, checking prices, conditional logic, all to produce one final plan.
Exactly. It's incredibly hard for the model to generate the correct solution, but it's super easy for a simple script to check if the final answer violates any of those rules. That's the perfect kind of data for teaching complex reasoning.
And on top of that, they improved how the model thinks while it's using those tools, this novel thinking context management.
Yes, this is a subtle but really important change. Models used to be very wasteful. After every single tool output, like a calculator giving a result, the model would just throw away its internal thought process and start over from scratch.
Redundant. It's like rereading the entire chapter every time you turn a page.
Exactly. It burns a huge number of tokens. The new rule is simple. The model's reasoning is only discarded when a new user message comes in. If it's just getting tool outputs, it keeps its train of thought.
So it maintains its mental state. That has to make it way more efficient in long agentic chains.
And the combination of all this, the massive synthetic data and the smarter context management, led to huge gains on agent benchmarks, really narrowing that gap with the closed source models.
Okay, so we've covered these 3 huge breakthroughs. But let's be realistic. This isn't a perfect model yet. What are the trade-offs? Where does it still lag behind something like a Gemini 3.0 Pro?
The biggest limitation, and it's a significant one, is token efficiency. The model gets the right answer, the accuracy is competitive, but it often takes a much longer path to get there. It generates more tokens.
Right. The sources had data on this. For the Codeforce's competitive programming benchmark, to hit a certain rating, the DeepSeek special model needed to generate 77,000 tokens.
And Gemini 3.0 Pro got the exact same score, needing only 22,000 tokens.
That's more than 3 times the computational cost for the same result.
Right. So DeepSeek proved open models can be just as capable, but not yet just as efficient in their thinking.
And what about just general world knowledge?
That's the other area. It still lags a bit in the sheer breadth of world knowledge because it was trained on fewer overall tokens than the absolute biggest models. That was a conscious trade-off they made to focus on reasoning and efficiency.
One last practical point. The model's context is limited to 128K tokens. How did they handle tasks like browsing the web that can easily go beyond that?
They used test-time context management strategies, basically clever tricks to work around the limit without changing the model. They tried summarizing old context, for example.
And what was the surprisingly effective strategy?
The discard all strategy. When the context limit was hit, it just threw away all the previous tool history and gave the model a clean slate.
Sounds brutal, but it worked.
It was highly effective. It showed that sometimes a simple reset is all you need to let the model keep making progress on a complex task.
So to sum it up, DeepSeek V3.2 is a landmark release. It has effectively reset the bar for what we can expect from open LLMs. By focusing on architectural efficiency and then just pouring resources into a stabilized post-training phase, they've shown that open source can challenge the proprietary frontier.
It fundamentally changes the conversation. And if you
Yeah.
think about the bigger picture, this success, especially that special variant getting gold medals, it brings up a really interesting tension. It all comes back to that 77,000 token number.
You mean they've proven they can be just as smart? The next question is, can they be just as elegant?
Precisely. Is the next frontier for open models less about raw architecture and more about optimizing what you could call the intelligence density of their reasoning?
Can they teach the model to be more economical in its thought process, to get that same gold medal result using 22,000 tokens instead of 77,000?
That's the next great race. That struggle for intellectual efficiency, for making frontier intelligence affordable, is going to define the next phase of this competition.